now that you have learned Faraday's electromagnetic induction and also Lenz's law, where you can figure out what the direction of the current is based on the potential difference, you can utilize those two rules, so electromagnetic induction and Lenz's law, to try to see how electricity actually can be generated. So it doesn't come for free, so we do have to take one form of energy and then transform it, so do some kind of a work in order to create electricity for us, so in order for current to flow. Now, in the AC video, so the one that I talked about alternating current, I kind of mentioned, okay, what you see here on the screen, and that is, you can very easily see how you can move a coil or a magnet back and forth and then create current, which is going to be flowing in one direction and another direction. So you can see that right on the screen, and I can put up a link up above there to the AC current. Now, I only did it in a very short, brief way to introduce to you that that is exactly what you can do. And in that sense, so I have utilized the PHET lab. And again, I'll put up the link in the description below, where you can take a magnet or a coil and move it back and forth in order to see that current is going to be flowing back and forth. And we've also used that for the induction of the current when we were talking about Lenz's law. All right, so I'll put up a link to Lenz's law over there. So within here, so for example, the idea was that we can just move a magnet back and forth, and as you can see there, the light bulb is turning on and the electrons are kind of going back and forth because of the fact that we're changing the magnetic field. Now, Lenz's law was all about trying to see that due to the conservation of energy, the actual current is going to flow in such a way that you're trying to resist the magnetic field change that is happening. And that is exactly what we're going to utilize in order to see how can we do this so that we can create electricity and generate, basically create an electric generator. So something that produces electricity for us. So it takes one form of energy, so maybe some kind of a mechanical work, okay, or gravitational work, or any kind of other kind of energy that we would have, and then transitions it so that we can have electricity flowing and we can use it within our households. So one other idea that you can utilize, so again, so this is from the same lab, so this is on the last tab. Okay, so here's a pretty neat generator that you have. Now, this is not necessarily the most common one that we would use in terms of trying to see and generate for huge amounts of energy, but it gives you this concept of what you can think about in order to transition one form to another. So you have a faucet here on the left-hand side, okay? And if you turn on that faucet, so notice that the magnet is actually on almost like a turbine. And when the water is flowing, okay, so it's going to force, okay, the actual turbine to kind of move around. And what it's going to do is it's going to move the magnet and therefore change the actual magnetic field, which is going to be going through the actual loops, so the coils that we see here on the right hand side. So I'm going to turn this on to give you a sense of how is another way that you can create, okay, electricity in general. So I'm going to move this so that it moves pretty quickly. So there's quite a bit of water which is flowing out. So again, you can think about so even something like a falls where the water is falling down. So we can capture and transition that gravitational potential energy of the water as it's flowing through, so it changes into kinetic energy. That kinetic energy can now start to turn the turbine, and on the turbine we can locate a magnet, and then that magnet is going to be changing a magnetic field. And if you have a change of magnetic field, then a coil beside it is going to have electrons which are going to be moving back and forth depending on the change of the magnetic field, and therefore producing electricity for us, or the flow of these electrons, as you can see there. So you have a compass, which basically shows you, okay, that it's kind of spinning around because it is a constant change in the magnetic field. Now, this is moving around, so relatively quickly. We can slow it down, as you can see here, so that you can capture, okay, and you can very easily see that these electrons are kind of just going back and forth through the light bulb. We can also kind of see it on a galvanometer, okay, within here, where it just kind of flip-flops between one side and another, where you can capture, okay, kind of the voltage potential difference. And if you have a voltage potential difference, you have the ability to flow, okay, and have a current. So I'm going to turn this up a little bit, okay, so a notch a little bit further. So here you go, we're going to max it out, and there you have it. So if you can spin it very quickly, you can see that you can produce the actual electrons flowing, or a current, to be able to flow. Now, in which directions the actual current is going to flow, that will depend on Lenz's law, right? So it depends on the fact that what the current will want to do is resist the change. Now, this is, again, not the only way. So you've now seen two things. You know, you can move a coil, okay, and you can move a magnet back and forth, or you can, okay, locate a magnet, put it on a turbine, okay, start to spin it around, and then we can generate electricity. And that's exactly kind of what we want to be able to capture. Now, another form of transitioning is, and this is the one that we'll dive into a little bit deeper, is going to be, so if you recall from a little while back, our DC motor that we had. Now, of course, the DC motor, we wanted to move the coil in the presence of an electric field, right? So we were moving this particular coil through actual electricity flowing through it. Now, what we want to do is, we don't want to have a motor, we want to do the reverse. So what if we started to spin the actual coil ourselves? So as you can see here, so on this, so I took this from Scientific World, okay, so huge props to them. So you can look up, and I'll put in the description below the full video. It's not a very long one, okay, but obviously way longer than the one that you see here on the screen. And what it does is it kind of goes in visually trying to tell you how the process works. And I will give you that idea from the viewpoint of someone who's just starting and doing foundational physics, so someone in maybe grade 11, or your foundational physics, okay, maybe in a post-secondary institution, where you're just trying to grasp the concept of, all right, so now I have the ability of understanding electromagnetic induction, right? So that's what Faraday has done. And I understand Lenz's law, which is, you know, which way the current might flow. Now, the third thing is, all right, what if I want to introduce and see produce electricity? What if we started to move the actual coils, right? And as we're moving it back and forth, okay, as we're going through, well, if you're going to move the coil and you are now at a present, so this is a fixed magnetic field, so from the north to the south, you know that you're going to be changing the magnetic field there. And therefore, if you're going to be changing the magnetic field that goes through the coil, that means there's going to be a current which is going to be produced. So here is an image, and this is, again, so from one of my favorites, okay, so again, I'll put it in the description. So within here, so this is from page 599 of the physics book, okay, from Nelson, and they actually illustrate this, and I want to be able to explain this entire concept. Because yes, you do have the ability of knowing, all right, now that I understand Lenz's law, in which direction is the current is going to start to flow. And this is not a motor, this is actually an electric generator. So as this thing spins, so notice we have an axis of rotation in here. So this rotation, as you would see, and this is going to be maybe hooked up to some turbine so that you can start to move this coil back and forth. Now this coil, as you can see there, so it is attached, right? So it goes all the way through within here, but it's attached to two slip rings. So here's one slip ring and here's another slip ring. And what we're trying to do is we're trying to rotate it around. So maybe, you know, this is from some kind of a mechanical energy, okay, as it moves this around. We want to see, okay, is the current going to be produced and in which direction? So now, if you move the coil, the current will be produced because you're changing the magnetic field. So now, if we're assuming that this is going to be moving in the clockwise direction, what will the current try to do? So remember, Lenz's law tells us that it's going to try to oppose the change. Oppose the change. So if you're moving this, so you have a force which is up, okay, and then this is a force which is down. All right? So you're going to have a force which is going to be pushing this because it's in the rotation, right, in the axis of rotation. So what you have as it's moving is something like this, right? So here is kind of a decimals figure that I have. And what's shown is, so here's a force which is upwards, okay, and then force which is downwards because this is rotating around the axis. So this would have been rotating in this direction, okay, and going that way. Now, how can it rotate? So first of all, notice that it can rotate because you have these slip rings. So on top, so with this piece on top and this piece on top, these are like brushes. So they are basically just touching these rings, but the rings can actually rotate through. And, okay, as it rotates through, so you have a brush which is on top, and this, because the ring is constantly rotating, is attached. So it will allow for the current, okay, to flow out in some direction, right? Now, this is going to be now attached to some external circuit on both sides. So you're going to create some kind of a voltage potential difference between these two, and therefore you can allow the current to flow. So again, two brushes are touching the rings. The rings are now spun around. Notice that one side is attached to one ring and the other side is attached to the other ring. So you can create a voltage potential between these 2 points. Now, if it is rotating in this direction, the easiest way to think about this without any kind of calculations whatsoever, remember that by Lenz's law, the actual current is going to be created in such a way to prevent the change. So to prevent the change, so yes, it is a change in the magnetic field, but if there is a force which is now trying to drive this upwards, now in order to prevent the change, then you will have a force that will be caused by a creation of a current which is going to flow so that it will oppose this force. Well, in order to oppose it, the force has to be downwards in here and it has to be upwards within here. So that's exactly what we want to be able to see. So in other words, if you take a look, so I have here the decimals figure. So I'm going to just turn on here. So those vectors, so here is 1 and 2. Those are the two vectors, okay, that we have. And those vectors, the red ones pointing upwards are the force, and then the opposing one is going to be downwards. Now, once you know that, so if you know that the opposition is downwards, this will tell you in exactly which way the current is going to flow. So if you have a force down in here and you have a force which is up here, to counterbalance, because that's what it's trying to do, it's trying to prevent this force from moving it in a rotation. So now you can just go ahead and use your right-hand rule. So now your right-hand rule, as you have, will now tell you, all right, in which direction is the magnetic field? Hold on, that's not very difficult for us to see because the magnetic field is from north to south. So we know that the magnetic field is in this direction. In other words, the magnetic field is now pointing in this direction, right? So here is our magnetic field. So if our magnetic field is in that direction, and maybe I will draw it out in here for us. So it's going to be in this particular direction within here. And our force is downwards, so that's our force that we want to counterbalance this. That's our magnetic field. Now you can use your right-hand rule to now decide in which direction will the current to flow. Now you can decide the current, or the right-hand rule based on the solenoid, so you can wrap it around, and it will show you that which direction that will be flowing, or you can use your right-hand rule to think about which way should the current go and then wrap it from the current to the magnetic field and then your thumb, okay, is going to point out in the direction of the force. So now if you look at this, so notice there's only two possibilities for the current itself. So the current can either go in this direction, so it can flow around, meaning, so it would have been flowing in this direction, right? So as you're going through, or it can flow in the opposite direction. Well, so test it out. If it is flowing in this direction, and you now take your right hand rule, so you point your fingers in the direction of the current, wrap it towards your magnetic field that you have, then what you will see is that you wouldn't get a force which is down. You would get a force which is up. So therefore, it cannot be in this direction. And it must be in the opposite direction. And again, you can use your right hand rule. From your right hand rule, you can go from the current to the magnetic field, and that actually indeed provides us a force which would be downward. So, as you have it, now you maybe have noticed this, I've already labeled the actual direction by little arrows that we have in there. So let me go back in here, as this I can actually rotate through. So you can see the little arrows that are pointing, and those are the arrows of the actual current. So the current is flowing, okay, in that direction in order to create the resistance against the change. Now, as it goes through, it turns out that this would have been the actual, so as you're going through, at the angle of 0, okay, so as when your plane is flat, so your coil is flat the way that it is, this is the highest magnitude of the current. And as it rotates all the way around at 90, it's basically at 0, okay, and then it continues on, okay, at here it's another magnitude, but it now changes, okay, so the current goes from positive to negative. That's what you have, and then it just rotates all the way around. So that's exactly, okay, what you are seeing, okay, within here. So if I go back, okay, to this diagram and to this, so I just want to be able to show you that what you will have is that your current, as this keeps flipping back and forth, okay, so that will be changing, okay, the current. So the direction of the current, okay, will continue on, but it's going to go in one direction and then turn over, and it's going to reverse. So depending on how the coil is. So within here, so it starts to flow within, okay, and then it goes all the way around. So notice that the coil is flipping over, right? So as it is flowing through, so it will go up and it will go down through 0, up and it will go down, because of the fact that there's a constant change. The same thing has happened within this simulation, okay? So this is exactly what you see here because of the current. So notice it's going back and forth, because the magnetic fields are changing. So there you have it. Okay, so this is the basic understanding of how electricity can be produced in a presence of a magnetic field by rotating coils. Now this is only one rotation, so one coil that we have, but of course, okay, actual full out. So if you scale this up to electric generators that need to produce quite a lot of current, okay, and power in general, well, it's not going to be just on one coil. So you're going to run into multiple things, okay, that you want to be able to increase the actual current. And in order to do that, of course, you can create more coils. So you can wrap around many more coils. So that's one. You can also increase the magnetic field. You can increase the also the rotations, okay, so that you have in here. So you can spin it faster, okay, if you wanted. Okay, you can put a soft core. So that can also happen. So you can wrap the coil around the soft core that you've seen before, so an iron core, okay, so that it increases, okay, that actual current. And those are the items that we can utilize to make the current bigger. All right, so that is it for this video. Okay, I hope that this gives you some kind of a sense and understanding of how current can be created. Thanks for watching.